All right, students, MC 11-1. So if you take a look, 1, 2, 6 to 10, 12 to 14, and 18 to 25. Now, the reason for this is, and you're going to see it here, when you start looking at it, you have a number of general pieces, and then you get to the ones from the classroom. The classroom ones are super important, and I need you to see the connections between them. So connecting math to the classroom, I want you to be answering these questions. These are typically some of the questions that do show up on a test. All right, so let's take a look at these as we go. So again, 1 through, what did I say? 1 to 2, and then 6 through 10. Okay. So in the drawing below, 2 distinct rays make one angle, 3 distinct rays make two angles. Continue in a conjecture about the number of angles determined with n distinct rays. We're not talking about reflex angles, only these. This is your chance to use all the things we've done with patterns. Looking at patterns, how many angles could we create? I would recommend that as you do this, you don't have to sketch everything out, but make it so that you can see the connection. How would you do that? Start with whatever angle you want. Here it is, right? So that definitely creates one angle, 2 rays, one angle. Now I make 3 rays. I can see 2 angles. So I start to think, oh, okay. So it goes 1, then 2, the next to be 3, then 4. But pause. That's very inductive reasoning. Let's see if there's a reason why that would be the case. So if I go to the next one, now I'm going to put 2 rays in the middle. I'm going to switch colors, or try to. There we go. So now we need to count how many rays there are, or how many angles are formed. Now we got to be careful, because now I'm going to go with all of the smallest angles first. So there'd be 1, 2, 3 smallest angles. Next up would be angles that cover 2 of these. So there'd be 1 here, and there'd be 1 there. So that's +2. And then don't forget the big one that I started with. Okay. So yeah, if you have 3 + 2 + 1, this turned out it wasn't even 2. It was 1, and this is, in my mind, strangely drawn. Not a big fan of this, but what they're trying to say is there's an angle here, and there's an angle here, and then there's a different angle here. Okay, that's what they were trying to share, which is actually 1 + 1 + 1, which would be 3, which is also the same as 2 small angles plus 1 large angle equals 3. You may be able to see a beautiful connection here to some things we've already done in this class. That's why I assigned that question. Next up, question 2. If 2 lines A and B are perpendicular to the same line, are those 2 lines parallel? Interesting. Now, again, your mind might be telling you to draw this on a piece of paper. The second you draw it on a piece of paper, you are assuming that the 2 lines are coplanar. It does not say that. This is the type of question that would be an always, sometimes, never question. 2 lines perpendicular to the same line must be parallel. Interesting. If they're perpendicular to the same line, what does that tell us? Okay. Remember, parallel has to be coplanar. Nudge, nudge, wink, wink. I am trying to push you with the terminology, and I'm also trying to push you in such a way that I point out the common mistakes that people make in this class. The common mistake is to think it's in a plane. It doesn't say it's in a plane. You can't assume that it's in a plane. All right. What's up next? 6 through 10. Okay, so this little block right here. Answer the following and explain your answer. How many lines can contain a particular segment? Okay, so if you think of a line segment, how many unique lines can contain that? Not how many ways can you name it, how many lines, unique lines. How many rays can contain a particular segment? Okay, now that is different. That's a very different question. Okay, and how many planes can contain a given line? Is it possible for 3 points to be non-coplanar? Interesting. This does go back to one of our axioms. All right, so I am trying to push, making sure that you understand these key ideas. Given a line and point not on the line, explain why there is only one plane containing the point and the line. This is not a bad way to think of, like, If you put the line as like the spine of a book or like a, kind of that kind of thing, and then you say, I'm just gonna tip the book along the spine until I touch the other point. How many ways can I do that? Is there a different way to do it? And I think you'll be able to kind of convince yourself that as long as that line is in one direction, maybe there is no other way to do it. You could also link back to our axiom about 3 points. How many points are on the line? Got to be at least two. So if you took those two and this other point, what does that mean? So you could connect it that way. How are pairs of parallel lines and skew lines different and similar? Great question. So if you watch the video or read the book, the definitions are in there, but now connect them. What is similar between these two? What is different? Okay, number 9, is it possible for angle ABC to have vertex C? Right, we talked about how we name angles. This is a good question that follows up on that. If planes alpha and beta are distinct planes having points A, B, and C in common, what conclusion can you make about points A, B, and C? Interesting. It's almost like they gave you something similar to that. It's not exactly the same because it doesn't have point C labeled. Clearly, this picture is for question 11, but it has plane alpha and plane beta. You can kind of see it. Plane A, B are here. Point C now has to be in common as well. That means it has to be part of the intersection. Where would that point be located? All right. And then let's see here. What else? 12 to 14. Okay. Now, 12 to 14 is a great opportunity for you to understand how the real world uses some of these pieces. So forest rangers use degrees to identify and locate fires. In the drawing, a ranger at Tower A observes smoke at a bearing of 149 degrees. Another ranger at Tower B observes the same source at 250 degrees. That is clockwise from the north. So when you're doing this problem, think of Tower B, here's north. 180 degrees would be here. 250 would be somewhere over here. And it gives you this idea that it's that direction. So using that, what we can do is just from those 2 points, we can find where that fire is located. Okay. And that's what you're going to have to explain. Explain why from that alone, they can do that. Okay. There we go. Describe other situation in which the location can be determined by similar method. So it doesn't have to be a forest fire, right? Where would this, kind of a similar method would be used to kind of find location? So if you can, that's some ask you to think. Maybe some of you have experience in other areas, and what a great way to share it. Number 13, is it possible to locate 4 distinct points in a plane such that the number of lines determined by the points is not exactly 1, 4, or 6? So again, 4 distinct points. That means they can't be the same. And they're in a plane. So if I go and do this, right, here's 4. And now my question is, how many lines are created? Okay, so remember we've done something like this before. There's 3 lines from this. Again, pretend that's right on there because I don't want to draw it. From here, we have 1 line here, 1 line here. So 2 there. And I get 1 more line coming down here. If I add all of those up, I get 3 plus 2 plus 1, which is 6. So that's one of the options. Then is it possible to have exactly 4? Is it possible to have exactly 1, right? If I put my points, 4 distinct points, that the number of lines determined by the points is exactly 1. Well, if you put all of them on the same line, right, then they are collinear. And that would be the 1. So I'm going to let you explore the 4. I've given you the 1 and the 6. And it's a question, is it possible? Could you do something? And notice it does say this time that the points have to be in a plane, right? So not just anywhere. All right, what else did I have? 12 through 14 and then 18. Okay, so 12, that was 13. 14, Mario studying right angles, wondered if his math class, if the hour hands and minute hands formed a right angle. Class meets from 2 p.m. to 2:50. Is a right angle formed? And if it is, determine the nearest second when the hands form the right angle. Hey, this matches right up with clock arithmetic and clock geometry. So Think about what we did in that section, how they move. They move at a specific rate. We're talking about the minute and the hour hands. So find a common rate that you want to use. You can do it by the minute, you can do it by the hour, right? Because the hour hand, if you want to do it by the, how far does it move? The hour hand starts up here and goes all the way around. And so that's 12 hours. And it makes it one full circle to 360 degrees. So if you divide that, you get 1 hour equals 30 degrees. Does that make sense? So every hour it goes 30 degrees, 30, 30, 30, 30, 30 to kind of get around all the way. So you could say that is also 1 hour is 30 degrees. You'd say 30 degrees per hour. But if you do that, an hour is 60 minutes. So if you prefer to do minutes, then just change that one and say, okay, so that's 60 minutes is the same as 30 degrees. Got it. Divide by 60, and you can say 1 minute is 1/2 degree, which would be 1/2 degree per minute. Okay. Use one of these two. I don't care which one. Don't mix them. Pick one. Because then you know the minute hand. So the minute hand, as it's going around, right? It goes around how fast? Takes 360 degrees in 1 hour. 1 hour is 360 degrees, not 30 degrees. They're not moving at the same rate. And then you can come down and say, okay, well, 60 minutes is 360 degrees, divide by 60. So 1 minute is 6 degrees. So this is the hour hand, and the minute hand is going 6 degrees per minute. That's the minute hand. Okay. And then, yes, you could say, well, I want, draw a picture to see which one's in front, and then use a variable. Use a little algebra here to say, I don't know how many hours it takes, or I don't know how many minutes it takes. So call it M minutes. So the minute hand is going 6 degrees per minute. So that means it's going 6M. That's how many degrees it's sweeping out. And it's going to make a big angle, right? And it's going to actually fly by at 2 o'clock. So at 2 o'clock, it looks something like this. Right now, it's a 60-degree angle because one of them is 30 degrees per hour. So it's 60 degrees ahead. But then this one starts up and it's going to pass it. So it's not going to make a 90-degree angle until later on in the day. But the minute hand is going to go past the hour hand. So make sure the minute hand is in front, and then you can subtract, and you want that to equal the 90 degrees. And all of a sudden you can create a nice equation and solve. It's not actually too bad. You can find exactly what it is. Cool. 12 to 14. Okay, then down here, I said 18 through 25. Okay, Allie says A, B, and C, D are parallel because they do not intersect. Look at this, though, and make sure you should ask questions. Allie, are these in the same plane? If they're not in the same plane, maybe they don't intersect. But remember, parallel is related to the line. A line is parallel to another line. Line segments are not parallel unless the line it contains is parallel. Okay, so make sure that's a key point as you answer. Bon named the line as ABC. How do you respond? Do we need ABC? Sometimes you put in a name and it's a little bit of overkill. So be thinking, what's the best way to name this one? And let's see here. Student says AB segment is not equal to AB segment because AB starts at A and B starts at B, and this one starts at B and starts at A. How do you respond? Now that's interesting. Notice the student has also put an equal sign between them. An equal sign should come between numbers, not shapes. So there might be a couple things that I would help a student out here. One of them being the symbol that is chosen. Remember, if you want shapes being identical, we'll use the symbol for congruent. This is used with shapes. This is used with numbers, and that helps you to tell the difference. Sometimes we're looking at numbers, sometimes it's the shape. Lou says a line segment has a finite number of points because it has two endpoints. How do you respond? Great question. Feel free to tie this back into the denseness property of fractions from chapter 6, 6.1. Student claims if any two planes that do not intersect are parallel, then any two lines that do not intersect should also be parallel. How do you respond? Keep in mind, I'm asking you to think. Just because it says two lines, it doesn't mean they're coplanar. So again, keep that in mind. Student says it's impossible to measure an angle since each angle is the union of two rays and they extend forever. That is true. The rays do extend forever. So the student's saying then you can't measure the angle because you can't measure something that goes on infinitely. So think about your response to that. And think about your response tied into the two different objects, one of them being an angle and one of them maybe being the length of a ray. Okay, so sometimes students do mix this up. Good question. Cade says to make the measure of an angle greater, you just extend the rays. Oh, there you go. Now the angle's bigger. This is a common one at the young ages because they see longer lines or rays mean bigger value. So think about that. What is right about that? What are they thinking about correctly? And maybe where is the issue? And then lastly, student says there's only 360 different rays because there's only 360 degrees in a circle. How do you respond? All right. So if you had a point, you could say, oh, there's one. Then I got one over here at 1 degree. I get another one at 2 degrees. I get one at 3 degrees. I get one at 4 degrees. You tell me, is it possible to have a ray in between these? That might help your explanation to the student. Phew. Okay. I don't think I signed 26. I don't think I did. I didn't find that question to be satisfying. So, yep, got that. This also, I've assigned a group work. I have, okay. Yeah, this one's a little deeper, so I'm not going to go into that one. Yeah, this one's a challenging question, so I did leave that one off. But part 1 in group work is assigned. So when you look in the homework, it says GW number 1, that's group work. You can work by yourself on this. You don't need to do everybody else, right? But use a protractor and make a triangle out of cardboard or thicker paper, whatever you can use, that has one angle measuring 30 degrees and another of 50 degrees. Again, here you want to use your straight edge to create straight lines. So when you cut it out, you're fine. Answer the following. How to use the triangle to draw an angle with a measure of 40 degrees. Okay. Now you'll notice a 50 degree and a 30 degree. You don't have a 40 degree angle anywhere here, but you might be able to find a 40 degree angle without using the protractor if all you had was a 50 and a 30 inside this triangle. Now you can rotate the triangle, and don't forget, just because you have a 50 and a 30, there's one other angle in a triangle. And you could use your protractor to measure it if you want. But if you're going to do this, I would recommend try to make it at least a couple inches on a side. So this is me trying to give you a push in the right direction here. So I would measure a length, maybe 5 or 6 inches, maybe less. So I'd say 4 to 6 inches is probably good. At one side, use the protractor to measure up 50 degrees. On the other side, use the protractor to measure 30 degrees and then draw those lines, right? And what's going to happen is those lines are going to intersect somewhere. And then use your straight lines, cut, and you'll be good to go. There's your triangle. Okay. What other angles can be drawn with this triangle? And what they mean is if I draw an angle somewhere using this, so I could draw a 50-degree angle now, could definitely draw 50. What I do is I just bring my triangle over, I put my pen or pencil along the edge of cardboard or thicker paper, and I draw like this, and I've got a 50-degree angle. If I rotate the entire thing, I could put it down. So this angle is now where that one was, and I could sketch it, and I would have a 30-degree angle, right? I'll do a different color here. So if I did rotate that around, I would actually have an angle look something like this, because that'd be 30 degrees. So what's great is you just drew a 50 and you just drew a 30. And for free, you picked up one additional angle. If the big one's 50 and the small one's 30, what other angle did you just draw? Interesting. I know, you didn't even need that angle, and yet you can make that angle. So that's kind of a nice one to have in your pocket. Sometimes you don't need to have everything built in to get other pieces. We can use our algebraic thinking to solve for it. Okay. Dum-dum-dum-dum-dum. This may come up later. It might come up in another section, to be honest, and I don't see it listed here. So I'm going to bring up a little piece here, and it relates back to an MC. There's an MC about labeling that line. Where is it here? Student. Student labeled the line. I think I got that one wrong there. Here, Bon. Okay, so Bon has labeled a line. So when you look at this, like when you are, okay. Oh, I have a new whiteboard. Oh, I don't know if I like a new whiteboard, but okay. Let's pretend. Okay, so here's my line. All right, that's great. And I'm just going to use my pen here. So I'm going to draw a couple points on it, right? A, B, C. A good question might be to ask you, how many different ways could I name the line, right? So I could name the line AB. I could name the line BA, right? And those represent the same line, of course. I could call it AC. I could call it CA. I could call it BC. And I could call it CB. So I actually see with just those points, I can actually name 6 different ways of naming the same line. But I might ask a different question. That is for line. How many different segments could I write? So my question might be something about how many segments, unique segments could I name? How many, and I'll put that in here, unique segments. How many unique rays? What a great question there. Because when you go and you say, okay, from a B ray, that's this ray, but BA ray goes that direction. So not exactly the same anymore, right? So you might have a different way you have to count those if you're looking for the unique rays. Okay, let me close this whiteboard. Okay, that's a new addition. Thank you, Zoom, for changing that. It's going to take me a little while to get used to it, but that's all right. Okay, so that's it for now. Hope you enjoy the rest of your day. Off you go.